Yes, I'm back. I'm sorry that just got disconnected. I'll run that again and I'll show you. Uh, Let me see. Although it was clear, but let me just run it one more time. Yeah, can you see the graph? Yes, are you able to see the graph? Okay, yeah. So I just hope the point I wanted to convey is clear. So you are just keeping on adding more and more terms from the series, and you see that actually the function contains sine waves because it's a sinusoidal functions. But long time behavior, you see, it behaves like exactly the function for which you're trying to write the Fourier series expansion. So the graph starts looking like the function for which you are drawing the Fourier series for. That was a graph that from this. This is the periodic behavior. So you are seeing the similar kind of graph appearing here, and this which you see connected actually. So these are actually connected because the sine x, sine 2x, they are continuous functions. So there cannot be jump discontinuity. But you see that connection to be almost turning into a straight line. So that will give you that, okay, there is a jump discontinuity because that's an approximation, right? So that was all about this graphical visualization. So let me just switch back to the our topic. Yes. So let me just continue with more examples for the same. Okay, so the next example which we are going to do this one is fx. Okay, so before just taking up, just a minute, just give me 1 second. Right, so now let me first, okay, let's do one more example, then I'll introduce the new concept. Okay, so your question still remains the same. Find Fourier series expansion of the given function. Now, how does this function looks like? So how this is different from the previous function? The previous function was given to us like fx is equal to x. So over the whole interval minus pi to pi, it was having a defined by just one function. But now our interval of definition is still minus pi to pi, as you can see the function, but it is given to you defined like this, that from minus pi to 0, it takes value 0, and from 0 to pi it takes value sine x. So at 0, although there is no discontinuity because the function value remains the same, so the graph of actually this function is like, if you talk about minus pi to pi, so from minus pi to 0, this graph takes value 0, and from 0 to pi this behaves like sine x. So this is like this kind of function, and after that it starts replicating its behavior, means it's given to be periodic. It's given to be periodic, right? So from minus pi to pi they have given you the function, and after that it repeats its behavior, it repeats its graph. Okay, so let me just do the calculation for this function. So you just, I'll be very quick now because we already know the formulas. So what is going to be a naught? So a naught is minus pi to pi fx dx. So this is only for, not only for this question, this is for all the other kind of questions in which your interval may be subdivided into domains. So the only difference this is going to create is while solving the integral, you will break the integral into parts, means into your domain. So it will be like 1 by pi minus pi to 0 fx dx plus 1 by pi 0 to pi fx dx. So as such, there is no change of formulas or nothing else changed. Everything remains same. It is just the way you solve the integral that varies. So that's very obvious. Wherever the breakpoint will be given in your domain, at that point you have to split up. 1 by pi, so minus pi to 0. Yeah, from minus pi to 0, what is the function value? 0. So this is simply 0. And the next term from 0 to pi, the function value is sine x dx. So if you solve this integral, the integral of sine x is going to be minus cos x. So I'm just directly writing the value. You can check the calculation yourself, not a difficult calculation. You solve the integral of sin x minus cos x, and then you substitute the upper and lower limit. You will be using here cos of pi. Cos of pi is minus 1. So using that, you will get your answer. So this is the value of a naught. And then while computing an, so while computing an also, you will be breaking this into two intervals, minus pi to 0 fx cos nx dx, and then 0 to pi fx sine nx dx. So from minus pi to 0, your function is 0. So the first term just vanishes and it is simply 1 by pi 0 to pi and sine x into sine nx dx. I've just substituted the value of fx from 0 to pi, which is sine x into sine nx. That is, sorry, just a minute. This is cos nx, not sine. This one is cosine nx. Yeah. So which formula you will be using here now to solve this integral? You can use 2 sine a cos b. So 2 sine a cos b is going to be sine a plus b plus sine a minus b. Right? So from 0 to pi. So formula which I have used here is 2 sine a cos b is sine a plus b plus sine a minus b, and that 2 was not there, so I have divided by 2. So this becomes 1 by 2 pi. And after this, it is simply solving the integral. So your integration gets two terms. Both of them will be having the sine integral is minus cos respectively divided with n plus 1. So very quickly I'm writing 1 by 2 pi minus cos n plus 1 x by n plus 1, and then plus 1 by 2 pi minus cos 1 minus n x by 1 minus n 0 to pi. Right. So you just solve this one. So the value of an which you will be getting, so it is 1 by 2 pi n plus 1. This minus can be taken outside, cos n plus 1 pi minus cos 0, and from here also we can take the negative outside, minus 1 by 2 pi 1 minus n cos 1 minus n pi minus cos 0. So minus 1 by 2 pi n plus 1. Yes, what is cos n plus 1 pi? So it will be minus 1 raised to power n plus 1, because we know cos n pi is minus 1 raised to power n. So cos n plus 1 pi is minus 1 raised to power n plus 1 minus cos 0, which is 1. And this is minus 1 by 2 pi 1 minus n again. So this will be minus 1 raised to power 1 minus n minus cos 0, which is 1. So you can leave it up to here, or you can further simplify to certain extent. So this will be 1 by 2 pi n plus 1 minus 1 raised to power, minus 1. This is there. You can take the negative inside. And from here, 1 by 2 pi n minus 1 minus 1 this. So yeah, so you can take the LCM 2 pi n square minus 1, because n plus 1 into n minus 1 will give you n square minus 1. So this way you will be getting minus n minus 1 into this plus into n plus 1. So you can further simplify if you want it. You can further simplify it. Yes, what is going to happen? Minus n into minus 1 raised to power n plus 1 minus n, and then there are two negatives plus, and this one will be plus minus 1 raised to power n minus 1 into n plus minus 1 raised to power n minus 1 minus n minus 1. So you see what is the answer? Yes, sorry. Is the terms getting answered? You simplify this and tell me the answer. Yeah, so this minus 1 raised to power n plus 1 or minus 1 raised to power n minus 1, because whatever is n plus 1 and n minus 1 are going to be of the same parity. Either both of them are even or both of them are odd. So minus 1 raised to power n minus 1 is exactly going to be same as minus 1 raised to power n plus 1. So these two terms gets cancelled because there is an extra negative here. And then there is this n gets cancelled with n, and uh, yeah, nothing else gets cancelled. So you will get the final minus 1 raised to power n plus 1 minus 1. You can write it two times because this and this, they are getting added up, and since they are same, so this is two times, and this minus 1 and minus 1 are getting added up, so this is minus 1. So this is two times 2 pi n square minus 1, so 2 gets cancelled, so it's basically this, right? So you will see from this question and in many other examples that uh, what gets difficult or what gets complicated is just these calculations, because the basic formula remains the same always for the Fourier series. It is just how you are comfortable in solving these integrals and up to what level you need to simplify. So I don't think so there is any further need of simplifying. This is much simplified. So that is what the expression for a and what you get. And I'm just giving all of you 1 minute to tell me the value of bn. Yes, I'm giving you all 1 to 2 minutes to calculate bn. So bn is basically, yes, what is the formula of bn? 1 by pi minus pi to pi f of x into sine nx dx. So this also you will break in two parts, 0 to pi, where it will take the value 0, the function is going to take value 0, and then, I'm sorry, from minus pi to 0 it is 0, and from 0 to pi it is sine x. Yes. So tell me the value of this integral. Solve this one and tell me what is the answer. Okay, yes, Vidushi, if you're asking minus 1 raised to power 1 minus n, so this is again same as 1 raised minus 1 raised to power n minus 1, because this minus 1 raised to power something just takes two values, either plus 1 or minus 1. So whatever is 1 minus n, the same is n minus 1 in terms of even or odd, because we only have to look at the even and odd, right? So that's why I actually had 1 minus n, but I changed it to n minus 1. But that is only possible in minus 1 raised to power. Otherwise, everywhere you cannot change it just like that. Yes, bn's value is turning out to be 0. So you verify yourself. It's not very difficult. Again, you can use the formula. So this is this time sine A sine B. So in the previous it was sine A cos B. So we used other formula. So this is this time product of two sines, two sine A sine B. So that is going to be cos A minus B minus cos A plus B. So this is the formula for 2 sin A sin B which we will be using, and then there will be two cosine from coming and their integral will be sine, and when you will be substituting pi and 0, so sine of something into pi, that is also going to be 0. So very easy to solve this integral, you will get the final answer to be 0. So now you just need to write, therefore the Fourier series is a naught by 2 plus summation an cos nx only, because your bn is simply turning out to be 0. So a naught we computed was 1 by 2 pi, sorry, 2 by pi. So this is 1 by pi plus summation n is equal to 1 to infinity. So whatever an we computed, yes, what was an? An was this 1 by pi n square minus 1 raised to power n plus 1 plus 1. Just a moment. 1 by pi n square minus 1 raised to power n plus 1 into cosine nx. So this is our final answer as a Fourier series expansion of the given function. Right. So after this, so we have done two questions of the same type, means the only purpose was to derive the Fourier series expansion, and the difference between two questions I already made clear, that it may happen the domain, the interval minus pi to pi is further subdivided into subintervals, and you just use that while solving integrals and you will get the answer. So after this, what we are going to do is, what if the period is not 2 pi? So far we have done two examples. Both of them were defined over the interval minus pi to pi, and both of them were periodic with period 2 pi, with fundamental period 2 pi. Now, apart from these, there are also functions which are having period something other than 2 pi. Their period can be 2, 2, their period can be 3, means it's not necessarily a multiple of pi. The period can be in the, the rational numbers also. The period can be 2 times something, 2 times L. So let me just write that. So if you want to compute Fourier series of fx such that fx is periodic with period 2L. L is not equal to pi. So something other than pi is there. It can be a real number, any real number. And the function is defined on minus L to L. So it's the same thing. It is just pi has been replaced with some number L, minus L to L. So what is going to happen? In this case, our formulas are going to change. To compute Fourier series of these functions, where the functions are defined on some interval minus L to L and they are periodic with period 2L. In this case, the Fourier series is given by a naught by 2 plus summation n is equal to 1 to infinity an cos. Now here is a change. It's not cos nx. It is cos n pi by L x plus Pn sine n pi by L x, where now there are changes in the formulas also. A naught is 1 by L minus L to L fx dx. So older formula for A naught was 1 by pi minus pi to pi. So this is now 1 by L minus L to L fx dx. An 1 by L minus L to L fx cosine nx was there, but now this time this is cosine n pi by L x, and bn is going to be 1 by L minus L to L fx sine n pi by L dx. Now actually these formulas have been derived using the same logic as we if we see the derivations of the Fourier series for periodic functions with period 2 pi, it is kind of, you can say, just a rescaling of variables, right? So with rescaling we get these formulas. Right now I'm not going to give you the derivation from where they are coming, but just to give you a broad idea, it's about the same thing we discussed in the previous lecture. Like we have a previous chapter, sorry, that we have a Dirac delta function, then we just shift the point of discontinuity. So instead of 0, it shifted somewhere. So that just gives a rescaling of the variables. So this is how this new Fourier series looks like, right? So these are the conditions that function will be given like this and the Fourier series is going to be computed like this. So let's do a very quick example for this kind of function. Right. So for this, we are going to do the first example. Find, the statement still remain the same. Find Fourier series of fx is equal to x square minus 3 to 3 and the period is 3. The period means the period of the function, or you can write it mathematically like fx plus 3 is going to be same as, just a minute, not 3 actually, the period is 6, because the length of the interval, so it's like minus pi to pi, so the period was 2 pi, so minus 3 to 3, so the period is 2 into 3, so that is 6, right? It is, you have to identify your L according to this. So this is like minus L to L, so your L is turning out to be 3, so the period is 2 times 3, which is 6. So whatever being the length of the interval, that is going to be the period of the function. So period is 2 times that. Anyway, we just need to identify the value of L, because for writing these formulas A naught, An and Bn, we just need to know what is our L. So yeah, let me scroll up if you want to note down the formulas again. Okay, so let's just do the calculation. So first thing is we'll compute A naught. So A naught is 1 by L minus L to L fx dx. So whatever being the interval given to you, it's very easy to identify L. L is 3, right? So it's 1 by 3 minus 3 to 3. What is fx? The definition of fx is given to be x square, as you can see here, x square. So it's easy to solve this integral. X cube by 3 minus 3 to 3. So 1 by 9, 27 plus 27. So basically this is going to be 6. So this is the value of A naught. Now we are going to compute An. 1 by 3 minus 3 to 3 x square fx into cosine n pi by L x. So instead of nx, it is now pi by L. So you can say these are the general formulas. If in these formulas we put L is equal to pi, you will get exactly the same formulas. So the idea is, you might think that, okay, we need to remember two formulas, two sets of formulas. It's not like that. You just remember this set of formulas. And in this, if you will be putting L is equal to pi, right? So you try this in these formulas. If you put L is equal to pi, you will get exactly the same old formulas, which are your original formulas, right? Because pi by pi will be just 1. So it will be cos nx sine nx. Yeah, so let me just do the calculation. So this is x square into cosine n pi by x by 3 dx. So this is, so you have to use obviously integration by parts here. First function into integral of second. In fact, you have to use it 2 times, because firstly x square will be going to 2x and then again one more time. So I'm writing the final answer. So you try this. Meanwhile, this is what you will be getting for the value of an. 36 by n square pi square into minus 1 raised to power n. So you try this. If you will not be able to get this, then I will be elaborating the calculation for you. But otherwise, it's just integration now. So you just use integration by parts, substitute upper and lower limits. You will get this is the value of an, and bn you will be getting as 0. Okay, so you verify this yourself. If somebody will not be able to get it, then you can let me know, because nothing changes about the way you do integration. The Fourier series is a naught by 2 summation n is equal to 1 to infinity an cos n pi by 3x plus bn sine n pi by 3x, because L is 3. So a naught which we have computed is 6. So 6 by 2 makes it 3 plus n is equal to 1 to infinity 36 by n square pi square into minus 1 raised to power n into cos n pi by 3x. Yeah, and bn is 0, so there is no sine term, there are only cosine terms. So that is your series expansion. What maximum more you can do is you can take this 36 by pi square outside the summation, and rest of the terms you can write like this. Right, so I just hope that is clear. Yes, any doubt? Next lecture we'll do just one more example of the similar kind, and then we will add to the next topic in the same chapter. So these questions are lengthy in the sense the way you need to solve the integrals. So, but you will see that there are fundamental trigonometric identities and relations which are very frequently used. So you need to just revise those formulas to get to these. Okay, so that's all for today. I'll see you the day after tomorrow. Tomorrow we do not have class. Okay, thank you.